We use your system in there.
How do you do? What version of Cassandra?
I can't remember. I'm from UPS.
Oh, okay. So,
And the concept.
is it Rob Batey?
Yeah.
So, yeah, I met him when he came into the talk at the Cassandra London Beta Group.
Yeah.
I'm currently talking to in the new area.
Yeah, we're going to use it.
It seems to be expanding.
Yes.
I think when I first went to Roll, it was Apache Cassandra, and then I started using Data Enterprise.
That's right. I belong to this group, so
I've just come from BCS, where I used to work for a number of years in heavy packages and heavy user, and they're just switching to Data Enterprise.
yeah, we use it across the number of different data centers. On the eventual system.
Yeah.
That's work. We had a failure. We had a work once.
Oh yeah, so when I used to build systems at Sky, we had like tens of millions of
Then I think we keep going. Well, John is saying that the only bit for us to retreat to the US, but I think 8 p.m. would be we don't have anything directly. Anyway, you can't get it with yeah.
I haven't thought of
And of course, the US anything very
Yes.
you're getting the Austin, Texas area, you get the West Coast.
Yeah.
They all operate more or less.
Have you all heard about the Cassandra London Day?
Yeah.
I do.
I don't think I've heard it. But my guys.
No, I should try and get there because there's a whole track dedicated to people who have already used this one.
We've got new project.
Yeah. So,
You know, I could think about it.
no,
That should be clear.
yeah. Anyway, we'll be around, we'll be finished. Yes.
What's the size of the biggest cluster?
It would be across 3 data center, 30 hosts, 50 server. This one is big to themselves.
Basically, you get the variety from 2 or 3 nodes to, you know, go and read about what Apple are doing with Cassandra.
Yeah.
It's just,
We don't use it on style. Big things. We have to use it. Our big data platform is still some specialized tabs.
but I do think that it's like different definitions of big data, but being able to handle just
Yes.
analytics being on that side.
Yeah, it seems to be quicker than mine. Everything.
Also for people who want to
Sometimes they need my journal.
just like
When a version of Data Enterprise comes out, it's based on Cassandra 2.1,
yeah.
big strides there. Strides.
Carry on. Yeah.
Yes.
No, go ahead. Just about to bring up an application, which application. This is, look, I've got the.
The syllabus exists on.
We're live, ready to go. Okay. Okay, it's very bright. It is very bright. I can't tell you why, but we'll there doesn't seem to be an obvious way of adjusting that. There's, you know, there's this.
Just Cassandra.
Settings here, but there isn't that. You can choose your camera, right, which you don't, but there isn't a way of adjusting the.
This is the basic concepts, I guess, which
In my opinion.
It's possible people like something that make a difference.
We have a lot of people striving for
Shooting accessories.
Yeah.
Cassandra was here with we got a few Mongols.
Yeah.
That's based, approach based and
No, obviously.
things like that as well.
It's interesting. I think they're very rare competitors. So
They're different use cases.
indeed, the main competitor for Cassandra is
It's easy for me to borrow bench rate.
it's the only one that actually
That's why I'm going to say.
Mongo Couchbase. Very good couch. Obviously.
We're good to get going? Yeah,
Yeah.
started. Jeff, is the video any good?
Yeah, we're good.
Cool. Okay, so just quick introduction. So we have tonight Christopher from DataStax. He's been working with Cassandra
For a number of years.
And I think DataStax is one of the major contributors to the Cassandra project, right?
That's right, yeah.
So lots of in-depth knowledge.
Mhm.
So I expect to be hoping for lots of questions as we go through, or do you want to help at the end?
I'd rather it be interactive, so yeah.
Cool. One thing that I forgot to mention last time, we have got another talk next month. So it's due to be predictive policing, so artificial intelligence for selecting criminals, I think. Should be very interesting. The DataStax guys have very kindly sent some what they call swag over, so some t-shirts and stuff outside if you want to take one. And thanks, Christopher.
Brilliant. So as I said, if you've got any questions as I'm going along, let's just pause and answer them, okay, rather than people lose track of what's going on. So it's a bit of a survey. Who's used Cassandra? Anyone here? I've already met one user. Anyone else? Who's heard of Cassandra? So quite a few. How about DataStax? Less so. It's interesting because pretty much the only documentation for Cassandra is on the DataStax website rather than the Apache Cassandra website. But hopefully you'll understand what DataStax are by the end of this talk. But more importantly, I'm pretty much only going to talk about open source Cassandra, not about DataStax. I'm not a salesman. Don't worry. You don't need to run away. So first off, I'll just go into quick introductions. So until very recently, I was building applications with Cassandra for BSkyB. So if you've ever used SkyGo or many of Sky's to pay me to come and contribute to an open source project, which I already worked on, and spend around the other half of my time coming and talking about Cassandra, because they're invested in it doing well. So first, we're going to talk a bit about motivation. So why do we need different databases? We've been using relational databases for, what are the use cases where they don't fit? And when would we want to use a database like Cassandra? Okay, but we're really going to go into depth. So the thing I love about working with open source software, or real open source software, is you can understand why it works. It's not a sales pitch. It's fast. You know, you take it, you can look inside it, and you can actually test it and then throw it away if you don't need it. So I love working with open source. Okay, so we're gonna go in depth into some of the details. Okay, and to understand how Cassandra achieves its performance, you kind of need to understand the details. And to run a successful Cassandra cluster, it's really beneficial to understand what's going on under the cover. But first, why do we care? Why are we building new databases? Does anyone want to guess how many Apache projects there are? I actually haven't checked this for a number of months, so this might not be right, but there's around 300, and over 100 of them are databases. And a number of them are new databases. Every time I talk to people about databases, they come up with another one that I haven't heard of. They ask, how does it compare to this? You know, the databases are coming everywhere, but why do we need different ones? And just to give me an idea so I can do better analogies, let's do the little survey of who's used what. Who here uses a relational database on a daily basis? Most people. How about graph databases? So say Neo4j, Titan. Yeah, so not too many on the graph front. Key values, so anyone use Dynamo from Amazon, DynamoDB rather than Dynamo? No. And document stores, so things like Couchbase, Mongo. Okay, so I'll be constantly trying to compare Cassandra to those. Okay, but none of them are really, none of the ones I've listed here are really competitors to Cassandra, say, apart from Oracle. That's the one they kind of, it's normally Cassandra or Oracle for that choice. So why do things need to change? So if you're building a very small application by yourself, let's say you've got a few users, you have a database, say some web application. It might start off looking very simplistic like this. And if where people work, do you have downtime during a release? Do you actually need to turn off your application at some point, even for a short time? Who does? A few? Okay, of course, if you deploy an application like this, you'd require downtime. And in many industries, that's fine, okay? I used to work for IG Group. We used to not allow trading for a certain time, so we can do our software releases like that. But eventually, you get to work for a company where you can't have any downtime. Surprisingly enough, people want to watch television in bed on their iPads all the time. And they get really upset when it doesn't work, regardless of what time of day it is. Especially in finance, in certain industries, they don't allow downtime. Netflix, they lose customers, okay? Amazon, if you suddenly can't add something to your basket, then people leave, they don't use it, they don't buy it. So there are certain use cases where downtime, even for releases or database upgrades, isn't acceptable, okay? And we generally design our applications by that, by deploying multiple versions. So some of the applications I deployed at Sky, we'd have 20, 30 instances running across multiple data centers. That's for capacity planning, of course, but it's also because we wanted to be able to handle nodes going down, disks failing, and data centers going down, okay? So we normally deploy multiple versions. I've only got 2 on here, because I only have a very small slide. And then we normally put a load balancer in front. But we wouldn't normally leave it in one DC either, okay? So this is a bit of a joke. I've never actually had a tornado hit a data center I work at, though one of my colleagues have. But I have had my data center be underwater for a week. So when I used to work for Morgan Stanley, if you worked in finance during the hurricane that hit New York, you probably lost your data center if it was in New York. We did. We didn't get it back for a week. We didn't use that data center for as long as I could remember. You know, we had a DR site, but it was passive. We had to actually have a mechanism to fail over, and we did it reasonably well. But there's downtime. And the only silly point I'm trying to make here is if you actually really need always uptime, is you do need to be in multiple data centers. However, during my career, the most common cause of outages, say so I lose like all of the hosts or instances of my database, my application in one data center, is not hurricanes, it's not tornadoes, it's actually people, okay? So invariably someone goes to upgrade some hardware, change some hardware, or make a configuration change, and something goes wrong, okay? So hopefully we're convinced that if we're going to deploy an always-on application, we're always going to have our website work, or our mobile app work, or our trading application work. We're going to deploy multiple versions of our app to handle hardware failure, to do rolling releases, and we're going to be in multiple data centers. But not many databases have been built with this in mind. There aren't many databases that you can deploy active-active across 2 data centers and actually have it work. Okay, if you've ever tried to do this with any relational database or most of the document stores, it's extremely hard. You end up with sharding, you end up with master-slave, that type of thing. So I always joke that if you really want to build an always-on application, it's pretty easy to build our side of it if you're a developer, okay? Developing multiple instances, stateless services that say use a cache for a session store, that's kind of a solved problem. What hasn't been solved so much is the database side. So let's see if I've lost anyone. Who actually deploys to multiple data centers right now? Yeah. Who could handle one of those data centers going down without downtime? Yeah, I could. It's good. Okay, so I'm going to convince you that it's not a hard problem if you're using a database which has been built from the ground up to support this, okay? Because traditional databases have always typically been master-slave. Why? Because when they were built, they didn't need to solve this problem. Most computing problems that say for building online applications would fit on a computer, okay? That's not really the case anymore, okay? And how master-slave works, in generally, you're going to have a single instance of your database, which is designated, all writes are going to go through it. Depending on the system you're using, reads might go through it as well, okay? But what you're going to do is run multiple instances behind the scenes, and either asynchronously or synchronously, depending on the tech involved, replicate them. So you're keeping multiple copies of your data. Eventually, the master will fail, okay? And there will be some failover process, be it automated or manual, might need operator intervention, but you're pretty much guaranteed some form of service down service. Additionally, the failover process is always something people are scared of, okay? If you ever go into a data center and ask if you can turn off the master, they might be scared. If you ask, say, oh, I'm going to turn off, say, my read replica, they just, nah, yeah, turn that off, we'll put on another one. But to ask if you can just pull out the cable of the master, then people start to get shaky. But there are some huge advantages to this architecture, okay? And the main one is consistency. Because if your writes continue to go through a single host, then you can basically get ordered consistency. You can decide what happened first. Each of the bits of data in your database, you can decide what the value is. The disadvantage is all of the writes go through a single point, okay? And that is both your single point of failure, but in general, it's also your single point of scaling. So once that node gets to a certain size, it can't actually handle any more writes. And of course, we can build bigger and bigger boxes, but it always hits a limit. And I don't like to use the term web scale because it's just a funny term, but essentially, if the thing you're building is the whole world can interact with it through the web, okay? You will hit a point if your business is successful enough where one computer will not do it. Worse, I'm going to use another buzz term, which is Internet of Things, if devices are pushing data to this service. There's no way in 10 years that it's going to fit on a single box, okay? So what's the alternative? So here's used things like BitTorrents, okay? Or peer-to-peer systems, right? That's basically where we don't have a master. We don't have a single point of failure, okay? The way I would characterize databases that follow this architecture essentially means I can read or write to any node. It does not matter, okay? And I don't have any special nodes. I don't care whether you knock down this node, whether you do a rolling release, whether you add some more. They're normally quite easy for operators because there's only one type of instance. There's nothing special in it. The huge disadvantage is consistency. So if you're suddenly allowing your application, us as application developers, to write to here and here for the same value, then who wins? Okay. So if you want to actually gain this type of, say, reliability, the ability to scale systems, the ability to handle hardware failure, do rolling releases, you normally then have to sacrifice something, and it's generally consistency. So who's seen this picture? Yeah. If you actually Google on Google Images cap theorem, you normally get this picture, which is why it's in so many people's slides. It's the first non-copyrighted picture. Okay. So we all steal it, so that's fine. Who's heard of cap theorem? Yeah. So what cap theorem basically says, it just kind of gives you a reality check. So you get three things to trade with when you're building a distributed system. Okay. You can pick consistency. And that's what we talked about, okay? That's what we were saying, that we can decide an order of events. We can decide what the value of this thing is. We don't have two nodes in our system disagreeing on the value of something. That sounds like an awesome characteristic if you ask me. But the thing is, it's very easy on a single machine. It's very hard when you're separating a problem across data centers, okay? Extremely hard as soon as you put a network in there, aka reality. Okay? The other thing we have is availability. And that's a simple one. It's a simple one to understand. That's basically, will my system accept, say, reads or writes? So we're talking about databases here. So, or will it reject them because it's worrying about, say, consistency? And the final one is partition. So partition tolerance. So what that one basically means is, if, say, all my nodes in my database, my system, are up, what happens if they lose connectivity with each other? Okay, it could be a network fault, or perhaps it was just too busy to respond. But being able to deal with partition tolerance is very important if you want to build an always-up system. Otherwise, as soon as the link between your two data centers goes down, your database ceases to work. And most databases that you use will fall into multiple categories because they have so many different modes to run in. Whether you run a single node, say MySQL versus clustering versus master slave, so I'll put some examples up here, but it doesn't matter so much because most of them will run in, can probably provision themselves along the bottom here. The AP databases, so the ones which want to achieve availability and partition tolerance, they're normally based on the dynamic paper by Amazon. And it basically means that you're deciding, when you're building a system, we're going to pick availability, uptime, which I kind of see uptime as availability and partition tolerance combined, over consistency. Okay, so if we were Amazon, we would rather someone lose something from their basket, and they buy 2 things and lose their 3rd one, then suddenly you say, sorry, can't complete your transaction at the moment. And when you give an example like that, it's pretty obvious why. So let's say you're Netflix. So Netflix is probably the 2nd biggest user of Cassandra in the world. They would rather you restart your stream of Breaking Bad or something, and you start 30 seconds earlier, so you have to rewatch 30 seconds worth of the thing, then not offer you the service. Okay? Same with Skype. Okay? If suddenly Netflix is unavailable, if they're in the UK, they might go to Skype and vice versa. So availability is normally king. And again, I normally just kind of categorize like, this is always up, this is kind of picking consistency. I don't normally nitpick too about these. And often when you're dealing with these type of systems, what you're normally trading off is consistency versus latency. So you can decide in these distributed databases, hey, I'm actually going to wait for full consistency, so my write's everywhere. But if you're deploying, multiple nodes and multiple data centers across the world, it takes some time. So at some point, you'd rather lose some consistency to, say, respond quicker to your users. Any questions there? No? So let's just talk about, let's forget about theory and start talking about what Cassandra is useful for. Then we'll talk about how Cassandra is actually built. So the chances are that you use Cassandra on a day-to-day basis, even if you don't realize it. Okay? If you have an iPhone, you're using Cassandra right now. If you've listened to music on Spotify, if you've played any games online, Netflix are one of the biggest users. So it's extensively used. It's used a lot at UBS, like we've just been talking about before. Also Credit Suisse, it's used a lot of ING. So it's used for anything. However, when you use it, you're going to lose some functionality that you're used to in databases. So in general, the characterization of things you use it for is if you're on a big scale. Because if your problem does fit on a computer, there's no point losing some of the functionality that you would get in, say, a relational database. And I normally categorize people who come into Cassandra into 2. One where the data model fits, and the other that just need it for its non-functional requirements. So let's talk about data modeling in Cassandra briefly. So the way you design your schemas in Cassandra, you actually get to pick exactly which node it goes onto. And you get to pick which things are located on the same node, and you get to pick the order at which it's stored on disk. Okay? So when you do a query against Cassandra, you can generally achieve it by seeking once on the disk, on a spindle, and then doing a sequential read. So that's why it can get its predictable performance, okay? Which means it's particularly good for ordered data, okay? So we're talking about time series data. That's why it fits so nicely in, say, sensor data, okay? So weather data, or it's why it's hyped up as being used as a big Internet of Things database, because most of the information that's coming from all these devices that we seem to like to build is time orientated. The other reason to use Cassandra, as I mentioned, is non-functional requirements. So you really don't care. You're just going to store something. You don't mind what it is. It might be a playlist or information about a movie. It might be a trade. But you need a database that is going to scale with your application. So when we started to use Cassandra at Sky, we've changed our name from BCS to Sky now. So we used to have a couple 100,000 concurrent users. However, the year before we had 100,000, and by the time we started putting the system in production, we had 500,000, and we were expecting up to 2 million concurrent users. Surprisingly enough, people like watching television on their phones. You'd have thought it, okay? So we picked it because we needed to be able to add new nodes and to increase scalability and increase the number of, say, transactions that were going through it and the quantity of data without doing anything complicated, okay? We didn't want to start sharding data and running master slaves and coming up with a management nightmare. The other thing that was really important to us was running it across multiple data centers. Okay, so I've mentioned that a few times. So Cassandra has been built up from the start with multi-DC deployments in mind. Okay, and we're going to go into that in detail on how that works. But essentially, without any particular effort apart from the networking between the two, Cassandra will cleverly asynchronously replicate between the data centers. So we're going to go a bit into the internals now. Any questions just on why you might use Cassandra? No? So we'll go a bit into how it works. So who here has heard of Amazon? Amazon are actually a fantastic company because they give a lot back to research, okay? And they publish a lot of the things they do. It might be a number of years after, but they really do publish a lot of papers. One of probably the most influential papers that they've ever published was the Dynamo paper. So this described the system that they internally built to do their shopping carts, okay, the baskets. Because they decided that, suddenly enough, they lost money when the basket service was unavailable. So they wanted to sacrifice everything else, have availability first, and then to be able to say trade consistency versus latency. And we're going to talk about all of the things in the Dynamo paper. Cassandra was built based off that paper, the architectural principles. Some things it used, some things it didn't. And we'll talk about how they differ, okay? One thing to note about Dynamo, it was a key value store. It was customer to basket, okay? No fancy data modeling here, no time series data. That ordered data on disk that I spoke about comes from a different paper. And I assume we've all heard of Google. So they spoke about the system they use for storing, say, website information, and that's called Bigtable. And they were nice enough to publish that as well. And so Cassandra is kind of the marrying of these two papers by Facebook, followed by 5 years of open source development where it's changed quite considerably, but the underpinning architecture is really quite the same. It's more the way you interact with Cassandra that's changed over the last few years. So we've talked about deploying to multiple data centers. So every node that we install Cassandra on, there's only one installable. Everything's the same, okay? But the first thing it does is work out what data center it's in, what rack it's in, and then when it stores your data, I'm going to talk about this quite a bit, it distributes it equally amongst the data centers, and it makes sure that, let's say you've got 3 racks in your data center. Anyone running AWS? Any Amazon Web Service customers? So a lot of people there treat a rack as a region, as a data center, and availability zone as a rack. So what Cassandra will do there, let's say you want to store your data 3 times. You want to be able to handle 2 nodes going down. Then it would keep a copy of your data on each of the availability zones or racks. So you could actually lose 2 entire racks or 2 entire availability zones inside AWS. The other massive advantage for Cassandra being data center aware is they don't need to be real data centers. So a lot of people run a set of Cassandra nodes to back their website or their app or the thing that's collecting sensor data, whatever you're using it for, and then they keep some nodes on the side, designated in, say, the analytics data center, and that's where they run their big, expensive queries on. And they could just be large, say, table scans, but more often than not, it's either Hadoop MapReduce or Apache Spark actually running on top of that. But you get really good workload out isolation. Does anyone here extract their data, say, daily or weekly or monthly, and send it off to a different department that's probably running a large Hadoop system? Anyone? We did, and it was primarily because we couldn't run those types of jobs against the operational system. It would slow it down, it would have latency, okay? But with workload isolation, with being data center aware, we don't have to do this. So here's the paper. I'm not expecting you to read this. I'm going to summarize it for you, okay? So to achieve this always on available system, what did Amazon have to do, and what has Cassandra essentially copied and built upon? So these are the important things, okay? So consistent hashing is all about being able to work out where your data is in these many nodes, without having to speak to them all. And I've got animations to show how that works, but essentially a client can work out where its data should be without having to talk to them all. The next one is replication. So it's all good and well being able to find your data, but if there was only one copy, then you're not really building a fault tolerant system, are you? because the first time you have to restart one node, you'll lose a portion of your availability. You know, some of that data will go. If that node crashes or the hard drive dies, you lose the data. So the next thing we talk about in the Dynamo paper is how to replicate data. That's where these strategies are all about spreading your data across different racks and data centers comes in. Surprisingly enough, when you build a distributed system and suddenly your database doesn't fit on a single node, then it's really hard to work out what the state of the system is. So we're not talking about data here, we're just talking about which nodes, which servers are in the cluster, which servers are currently joining, which servers are leaving, which is up, which is down. So there's this concept of gossip. So this is basically where a node constantly tries to chat to its peers and they all compare state. And you can actually go to each node in Cassandra and see what their view of the world is, which doesn't make sense if you have, say, a 2-node database. You think, well, they should just know. But when you have a 1,000-node database, so at DataStax, we take Apache Cassandra and test it at the scale of thousands of nodes. If you can actually go and look at some of the videos from our last conference, the last Cassandra conference, and you can watch Apple talk about their scale. Okay, so I always now joke that you have scale and then you have Apple scale because they have 400 million users. And there's a few things which Cassandra didn't include. So who's come across vector clocks? So that's just a way of solving the problem that we write the same value for the same key, say for a key value store, on 2 different nodes. How do we work out which one wins? I'm not going to go into vector clocks because Cassandra doesn't do them, but we didn't use them, and I'll explain why later. So we'll start with consistent hashing. So the first thing you can think of when you talk about a distributed database, right? We're on many, many nodes, and we're going to add more nodes. So there are certain features which will be missing from Cassandra. Things like joins, group bys, aggregations. And that's because those type of operations do not scale. They scale to a server. They might scale to 2, if you're lucky 3. Okay? You'll not be able to do anything which requires any form of full table scan when that table is distributed across many nodes on a network, possibly separated by the Atlantic. Okay? So consistent hashing is all about a client or any node in the Cassandra cluster being able to work out where data lives. And I have an example in a table and a picture, because some people learn better from the table, some people learn better from the picture. So let's have a look at this. So let's say we have some data, pretty simple data. We've got Jim, we've got his age, he's got a car, and he has a gender. Another thing to note here is that columns aren't mandatory in Cassandra. You can have different columns per key. Okay? What we do is we take the key, we call this the partition key, and we hash it. Default it's number 3, but you can plug in your own strategy there. That will give you a number. Now I'm not using the real values because that's a 128-bit number, and I don't know how to say this. So I'm scaling Cassandra down to pretend that there's actually only 1,000 hash values. Okay, which means you can only put 1,000 things in your database, but let's not worry about that. The real number is very big. So we would take Jim and we would hash it, and we would work out this number, 350. And we do the same for them all. Okay? Each node in a Cassandra cluster owns a range of that hash ring. It's why you see Cassandra always as a ring, because it goes all the way from 1, all the way bound to the top again. Okay? And I have a picture to show that. So let's say we have a 4-node cluster, a very modest Cassandra cluster, and they own a range each. Okay? So this looks a bit like this. So we go from 0 all the way around back to 999, and then we overlap. Just imagine those really big numbers though. So we can see exactly where the data would lie. And node B owns, from 249 all the way back to 0, the previous one in the ring. Which means that any node in the cluster or any client, any driver that talks to Cassandra can work out which node it has to go to. And you don't have to go to that node, because if you happen to go to the wrong one, it will forward your request, because the node itself will do the same algorithm and send you there. Does that make sense? Yeah? Some of the questions I often get at this point is like, how do you add new nodes? Or how do you remove nodes? Because all the ranges change. And we'll go into that at the end if people are interested, but it used to be hard and now it's really easy, but we'll talk about it. The next thing we should need to deal with is replication. Because if all we did was store it on that one node, we wouldn't be very good, would we? It wouldn't be a particularly great database. Okay, we'd be back at that single point of failure. Okay, so the next thing Cassandra does is replicate your data. And it has a strategy for doing that. And I've touched on these. You have a very simple strategy. This is one you mainly use in development, so you do not have to tell your development machine which data center and rack it's in. So that's pure development. The more interesting one is the network topology. So that's essentially what I've discussed. That's what I've been hinting at. So that will pick the first one based off the hash, then it will walk around and look at the nodes, and it will find, say, a replica which is, say you want 3 replicas in our EU data center. It would walk around and find 3 replicas that are on 3 different racks. Okay, so if you were to lose power to a certain rack, you would not lose all of your data. So it's slightly cleverer about it. Obviously, if you have more, if you want a higher replication factor, because you pick this, you can pick 1, 2, 3, 4, 5, depending on your paranoia. If you have less racks than replication factor, then it's going to have to put multiple ones on the same rack. It's not going to magically spawn racks for you. So let's see how that looks. That's where the animation isn't going to work on the PDF. So what we've got here, we've got a 2 data center Cassandra cluster, okay, and a replication factor of 3 in each data center. So that means we're going to have 6 total copies, and we want 3 in each data center. Okay, so imagine this could be 2 data centers in the EU for fault tolerance, or it could be a data center in, say, America and Europe, you know, so clients can connect to the closest one and avoid the latency that is the Atlantic. So what's going to happen? Client can connect to any node. Let's pretend it just connected to any old node. That one is designated the coordinator. If that's a replica for the data, it actually owns that bit of data. When you do this, you actually choose a consistency level. Now, I always wonder whether to talk about consistency first or replication first. They're kind of intertwined. But we're going to talk about the simplest type of consistency first, and that's 1. What that means is essentially, Cassandra, return to me once 1 replica has the data on disk. Okay? It's not going to change how it replicates the data. We're still going to replicate to 3 nodes here. 3 nodes here. But what you get to pick is latency. You get to pick how long you're going to wait as a client. You know, and sometimes you just want speed and you're going to trust the asynchronous replication. But sometimes it's of a certain parts of data, you want to make sure that it's written to, say, 2 disks or 4 disks. Or perhaps you just want to write it at a consistency level where you read your own writes. So you don't, like, you know, talk to this node and then read it off another node and it not be there. Well, let's follow this through. So because we've done consistency level 1, we can return to the client right away. It's then this guy's job, the coordinator's job, to then replicate it in his local data center. Okay, so we're assuming a LAN here, or assuming a reasonably expedient network. So he sends it out to the other 2 replicas. The next thing it does, and this actually happens this all happens in parallel. It's just the fact that I need to describe it in a certain order. Is he designates a coordinator in the remote data center. Okay, so we're not, even though we need 3 replicas over here, we're not going to copy it over, say, a WAN, an expensive slow network 3 times. It's going to get copied once, and then eventually we have a write. Okay? Any questions on that? Because it's quite different to dealing with, say, a regular relational database where you're dealing with a single server. Yes?
If you have many repeater rings, this would be still quite expensive. So,
Pardon, so the question was, what happens if we had many different data centers?
yeah, that's right. If you have many such rings of different data centers.
Okay, so
because the same, so you are replicating the request on each different group, is that right?
absolutely. So it's up to you how many data centers you want to be in. So as we've talked about, there are 2 reasons for doing that. One is data locality with your clients to avoid latency. Okay, so probably apart from Apple, the biggest deployment for Cassandra is Netflix, and they're spreading around the world. They use 2 data centers in America, 2 in Europe, and then they're expanding out. You know, so that's close enough. So maybe it's 6 times, 5 times. But then you can also choose how many replicas. So it's kind of up to you how paranoid you are. how close you want it to be to your customer. But yeah, the more replicas they have, the longer it'll take, the more disk you'll use. 3 is by far the most common replication factor per data center. Okay, and that's basically because you can, if you want to say, if you want to read your own writes, you would want to write to 2 of those and read to 2 of those. So you always really want an odd number when dealing with like majorities and quorums. And we'll talk about consistency. We'll talk about consistency more now. Yes?
Do all the replications come from the first control node, or does it cascade?
So it's each write will be sorted out by one coordinator in each data center.
But you've gone from A to B. Does another one go from A to C or from B to C?
No, so inside a single data center,
Yep.
it is like, I don't want to use the word C, but C to everyone, so one to many. The only time that's not the case is when you want to get it to over a WAN, over a wide area network, over a slow network. That's when it will go to a remote coordinator in the other data center, and then he'll do the replication.
But if they're all on a remote slow thing, suppose you've got 100 out there all slow, do they all come from a central one, or do they?
So you would never deploy your nodes, individual nodes in a cluster geographically.
Yeah.
You would keep, say, 10 nodes in the EU data center, like a single data center, and that would be the data center which all of your EU customers would use. Okay. Then you'd use another data center, say in Asia or America, which would have some very close nodes.
Yeah, sorry, I mean, suppose you've got 100 data centers. First node sending out to one of them. Does it have to send it out to each 100, or do they start sending it to each other?
So the max kind of number you're going to get to for data centers might be 5 or 6. That will cover the whole world. So the answer was it would be the first one, but the answer is normally we have a very small number of data centers. Okay. Yes.
Can each node act as a controller?
Absolutely, yeah. So
Anyone?
anyone for any request. And we want to talk a little bit about load balancing in the future, and it's important that it's important that you don't assume it's a replica, because if you get hotspots in your data, you might not want to use. Say there's a really important customer, Chris, and he's stored on these 3 nodes. You might want to stop going directly to those nodes and let another node in the cluster be the coordinator. But we'll talk about that in a bit. And then, because I think all tech presentations need cats, I'm going to put one up, because I have to really hammer this home, because this is very different from virtually every database out there, okay? And it's just what you asked. Every node is completely equal. They own different segments of the data, and that will be shuffled around as you add and remove nodes. But that coordinator is not special. For that individual write request it is. It will do that write, and if that fails, it's the client's responsibility to try another coordinator. But you can load balance them across all of the nodes. We can have nodes go down, we can replace nodes, you can treat them, a common often phrase, you can treat them as cattle, not pets, okay? You can add nodes, remove nodes, etc.
So if each of the nodes is responsible for a given slice of the data, does that mean the client has to connect to the correct node in order to write?
It's up to the client, so you configure it in the load balancing policy. So if it does, great, we've got less latency. We've avoided a network hop for replication. If it doesn't, then the node you've connected to will just act as a coordinator and replicate it to the 3. And obviously the same applies for reading. It will ask the right replicas for the data. And there are circumstances when you won't want to use what we call a token-aware load balancing policy, where you always go to an actual replica, but not many. It is the default, it's what most people use, because it avoids a network hop. If you're using consistency level 1, you don't have a network hop before your read or write is finished. Okay? Yeah.
So if you're using a hashing thing to identify a node, and you have replication, are you going to have 3 nodes that are kind of identical?
Yes. However, the reason it's not quite so. I normally go into this after, but essentially you don't own one range. It's actually split into hundreds and hundreds of little ones. And it ends up being quite different to that in reality. And that was added reasonably recently, say last year, to make it easier to add and remove nodes. Because if you think about it before, if you were to add a node into the cluster, where do you put it in that range? Does it go in between 2 and take half? That's easy with a picture. Bring the picture. I'll have another one. Oh, I've got to go from animation. No. But essentially, it's lots of little ones. But yeah, you do end up with nodes with similar data. That's why you want each of those, one in each of your racks.
So if you're hashing to a particular node, are you always I mean, it seems like you could access any of those, but are you always going to be going to one? Or
No, so with the cat, so the algorithm for hashing, plus deciding the other nodes, like the replicas, we'll call them, is everyone can work that out, including the client. So even though you hash it and that's your first node, you then apply a deterministic algorithm to work out the other 2 or 3 or 4, depending on how many you picked. And then you actually can go to any of them. None of them are special. If the node is down, which you originally hashed to, it does not matter. And actually, the load balancing gets quite interesting here because you'll normally have what's called a token-aware load balancing policy. What that means is we go to one which owns the data. Could be any of them. It doesn't actually just mean this one. The next layer, the kind of like you stack them on top of each other, is the latency-aware load balancing policy. And that's where the clients themselves actually keep a track of how quickly they've all been responded. So you actually pick the one which is responding the quickest, okay? Or you can put it like the other way around and just do pure latency awareness, talk to the node which responds to you the quickest. Does that answer your question?
Yeah.
Are these nodes virtual or physical?
Either one. So lots of people deploy in Amazon Web Services, lots of people deploy in Google Compute Engine and Azure. At Sky, we deployed on Amazon and we deployed with Cloud Stack on top of our own hardware. The guys who want the best performance will roll their own hardware and deploy it directly on tin. Less flexible, but you avoid the virtualization. Yeah, the big thing to notice if you're thinking actually about using Cassandra, yes, you can put it on virtualized nodes, but never put your storage on network storage. Because Cassandra is very much about ordering it on disk. If you're using spindles rather than SSDs, it puts a lot of effort into only doing sequential reads and writes. So if you then, put it on some network storage, you actually put it on your extremely expensive SAN, you'll get much worse performance because of the latency over the network and the fact that the actual drive is shared. So in Amazon, if you speak Amazon speak, you generally use ephemeral storage, the actual disks attached to the machine. Any more questions? No. We've touched quite a bit on this because we were talking about consistency, but the example I showed was one. It's going to be the quickest. There's actually an even quicker one called any, which basically means, I don't care, you just sort it out. It actually, we'll talk about hints later, and that's where any becomes useful. One you'll never use is all. As soon as you use all with Cassandra, you're essentially as fault tolerant as a single server. Because if you want all 6 of those replicas to be up and respond to you, as soon as you're restarting one or putting a patch on the operating system or any reason it wouldn't respond, your query will fail. So all is not normal, but if you really want to do it, it is there. The most popular are majority-based, so quorum. So we have 3 replicas. Actually, we had 6 replicas in that example, didn't we? 3 in each data center. Quorum would be 4. The bad part here is 4 means we have to go over to the other data center, which is generally going to be slow. You're talking about round trip, 120 milliseconds between here and say the US. Okay, so in general, you don't want to use quorum. But what you might want to do is use a local quorum, which actually says, I'm my application, whichever node I've connected to, and you can tell it to connect to only ones in the same data center, get it to a majority in this data center, but just asynchronously do the other data centers. Okay, so that's a good balance. Okay, if you then read and write at local quorum, you're always going to read your own writes, but you're not going to have to jump over the wide area network over a high latency link to achieve your read and writes. But probably the most common actually is probably 1, because generally people who are working with Cassandra are just after availability and performance. But we use a mixture, and you pick this per query. So like certain queries for last application I built would be at 1, and some of them would be a higher consistency. We used to store audit events. What have our customers been up to? And we used to bill off that. So that we had it at higher consistency. We wanted that to be on at least 2 disks before we went away and said, yeah, that's recorded. And if you want a really good talk on eventual consistency, and I'll share these slides so you can have a look, is this guy is he's like lead cloud engineer at Netflix. And he just did a really good hour talk on eventual consistency. And what it's all about is they have their Cassandra clusters distributed, I think, in 5 data centers around the world. They actually write at 1, but then run tests to see how quickly the data runs out of each. It's just really fantastic. And then they keep doing the same while, knocking down a third of the nodes. But that's a really good talk to watch if you're getting into these kind of eventually consistent databases. So what we end up with, if we build with our application with Cassandra, is we deploy multiple versions of our application to make sure that's highly available, and we deploy nodes in each data center, okay? And by default, of course, we'll get these ones to talk to these one and these applications to talk here. But then if someone doesn't like Cassandra and they decide to turn all these nodes off, then these guys can flip over. And that works via load balancing policies. So the first thing I noticed when I moved to distributed databases rather than, say, relational databases, so single server or at least one master that my application is speaking to, is drivers are vastly more complex. Okay? What did the driver use? What does your typical Oracle JDBC driver do when you're running, say, a master slave, a few read replicas? It's talking to maybe one node for writes and maybe a few nodes for reads. It's pretty simple, right? What do you think a driver does in a database that has hundreds of database nodes that it needs to constantly try and keep track of who owns what data and try and go to the one which is responding the quickest? It's vastly more complex, but it gives you, there's lots of, if you use one of the newer drivers, these kind of things are in like the Python, the Java, the C++, Node.js, there's quite a few. And they all have these pluggable load balancing policies. That's where we get to pick how this works, okay? So data center aware policy is very important as soon as you go multi-data. Okay, we do not want to hop over, well, maybe they're next to each other, but in general, you don't want to hop over to the other data center, okay? What have we got next? We've mentioned there's lots in questions. We know what this one is. It's going to work out where the data is and go to that one, okay? And then, of course, we've got the latency. So that basically means it's going to start keeping track. And it's very common to use all three of these in one go. So I'd say I want to pick one in this data center that has a token for my data, it owns my data, and has responded to me quickly in the past. Make sense? There's actually one called the whitelist policy as well, which I've actually no idea why you'd want to use it. Maybe it was some way of doing some workload isolation that you needed more granular than data centers. But in general, everyone I've talked to uses data centers for workload isolation. And with combining these policies, we get nice things like this. You can upgrade all of the nodes of Cassandra in a particular data center with zero downtime. Okay, but let's say you're feeling lazy, you did decide to turn them all off, or someone did, destroy some hardware, or something just went wrong, or perhaps it was just the network connectivity between your apps and the Cassandra nodes. Then the load balancing policy talks to nodes in the local data center unless they're all gone. Then it will decide to move over to the nodes in the other data center. So there you're picking availability at the cost of extra latency. Okay. If your actual applications are not running, okay, and you route your clients to your other data centers, then everything's going to work fine, assuming it's suitably scaled, and the asynchronous replication is going to continue to happen. Okay. If we're doing things at local quorum, we're not going to wait for it to happen. But when we do get the data, when we do get these back up, they can assume that data written here is here minus the speed of light plus some minor overheads. Okay, and that talk there from Christian from Netflix is a brilliant one to watch if you want to see this one in action. If you lose the entire data center, then that's what happens when a hurricane hits New York. So, any questions? I'll hide that one because normally that's a question. Okay, so it's great. We can handle hardware failure. We can handle entire data centers being down. But how do we get ourselves back into a consistent state? How do we get those nodes back up to date? Because in general, we were talking about many computers and we're talking about large data sets. We can't use diff, okay? It's not going to work. So essentially, there are two ways that Cassandra gets you back into a good state, and both of these are from the Dynamo paper, okay? The first one is called hinted handoffs. So we think back to that animation where the coordinator needed to forward it to another node, another replica for that piece of data. What does it do if that node is down? And with the default configuration, it does not throw it away. What it does is it keeps hold of it. It remembers that that node was down when that write tried to happen. And when that node comes back up, it sends it to it. This doesn't happen indefinitely though, because if you're having a bad day at the office, and for some reason a good chunk of your servers are down inside your data center, then you can imagine that this hinted handoff, it actually adds some efforts. It puts some work onto the coordinator, right? It's storing extra things, okay? So there is a time limit on that. It won't keep doing it forever. Default, it's 3 hours, but that's configurable. At which point it will just start throwing them away. You know, at this point, it's expecting that it's going to be, after 3 hours, it's expecting it's going to be down for some time before it comes and fixes it, or you come and fix it, you get woken up, okay? And the way you get the Cassandra cluster back into a good state then is when you have fixed the nodes and you brought them back up, you just tell them to do what's called an anti-entropy repair. Okay, I'm not going to try and say that quickly. Okay, what that basically does is you say for all of the partitions you own, node that has been down for more than 3 hours, could you please talk to some of your peers and make sure you've got the most up-to-date data? Okay, now this could be vast quantities of data, so it can't transfer what it's got over to the other node. This could be terabytes, and then say, could you give me what I don't have? So it does it with good old Merkle trees. If you haven't, don't worry if you haven't heard of Merkle trees, but essentially it uses a tree of hashes to work out which bits it's missing, and then it requests those small bits. Now, not many people are going to be interested, if you haven't used Cassandra, about incremental repair. However, you might get UBS because it's a massive thing in the latest version of Cassandra. So previously, let's say you built up many terabytes of data. A repair would fix the whole thing every time. Now, you can imagine this takes a long time. You're calculating the hashes of the things on disk, right? And then you're sending over, even the hash itself can be very, very big. It's a whole tree of hashes, okay? So the newest version of Cassandra doesn't do that. It keeps track of which sections of data. Actually, it just sounds like common sense, doesn't it? It keeps track of which bits of data, which files on disk have been repaired, and then it only looks at the new ones. So your repair time becomes proportional to how much new data you've got since your last repair, not how much data you've got. Which is, if you use small amounts of data, you're talking like 100 gigabytes a node. This will not affect you whatsoever. But the people who worry about this are the people who are putting petabytes inside Cassandra, where a normal old school repair might take a month. So some people really care, some people won't. So the next thing is gossip, another thing from the Dynamo pig. And this is Cassandra's way of keeping track of everything that's going on inside the cluster. Which nodes have joined, which ones have left, who owns what data. Basically, if you've got a 1,000 node cluster, you cannot talk to everyone. If every node tried to talk to every other node, again, not scalable. So what it does is every second, it talks to a number of peers at random. And it says, what do you think the state of the cluster is? And they respond, oh, this is my state. And then they reconcile. Okay? And you can go to each node in the cluster, and you can say, what's your view of the world? Who do you think's alive? Who do you think's dead? So you'd be able to see, if you're trying to diagnose, say, a network partition, you'd need to see who can see who. And there is a tool called OpCenter, which can give you a global view, if you were sick of going to your 1,000 nodes and running a command line like that. So you can get them all to push this data out to a management tool. So scaling. We've touched on it a little bit, but how do you add nodes to a Cassandra cluster? Okay, so this is where I normally start talking about the fact it's not one range. It's lots and lots and lots of tiny ranges, assigned not quite at random, but there's an algorithm for it. When a new node joins the cluster, he has no data. He is a useless node, okay? But what it does is it talks to a number of the nodes, we call these seeds, and he says, I'd like to join the cluster. Can you please give me some data? And the cluster will work out and take a small amount of these small little ranges from a spread around the cluster and give it to this new node. It's called bootstrapping. While this is happening, this node will not accept client requests. Clients won't redirect request to it. It'll still go to the people who originally owned those little bits. Okay? When it's got all of that data, then, because the drivers in Cassandra are constantly chit-chatting, it's a two-way protocol with a various number of Cassandra nodes, they'll be alerted about that new node, and then client requests will start going there. Okay? Any questions on that one? Because this works nicely, but if you let your nodes get too big, you know, imagine if you've got 100 megabytes per node. Bootstrapping a new node pretty quick, okay? Terabyte a node gets slower, okay? So people say when you're scaling a Cassandra cluster, you'll do it quite early. You know, you won't leave it until it's at that point of creaking because, you know, someone's put your website on Hacker News or they've talked about it on BBC News, who knows, okay? So you scale quite early in Cassandra. This is a study, again, done by Netflix, where they just wanted to see how far they could take this. So not on their production environment, not in their actual application, they just started running a distributed load test against a Cassandra cluster. And while they were doing that, continuously added new nodes. Okay, so I had the overhead of the new node joining, and they just saw how long does it scale in a linear fashion for. And then they got to 1 million writes a second, and then they gave up. Because, I don't know, they ran out of money. But they didn't, they actually carried on with this. Does anyone read the Netflix tech blog? Okay, forget about my talk, just go and read the Netflix tech blog. It is absolutely fantastic. Like, if you're a Java developer and you use a lot of the modern libraries, a lot of them, like some of the Spring libraries, they're contributed by Netflix. They're awesome in this space because they need to build an always-on system. And what they got up to 1 million writes a second, and then they started knocking down nodes at random to check the availability. It's another. That one doesn't have a talk, but it has a long tech blog on what they're up to. So, any questions? Anyone getting interested in Cassandra? Want to go have a play with Cassandra? Hope so. It is fun. I almost, because I built systems with Cassandra for the last couple of years, I almost forgot what it was like to have to worry about a server going down or a hard drive dying. Or someone was showing me a demo of an unnamed database, and they were showing some dashboard. And they knocked down one of the nodes, and they said, look at our awesome dashboard. It shows that 25% of the requests are failing. Why would it? You know, you should be advertising this. Okay. With Cassandra, it's not the case. It's an ops people tend to love it once they get to know it. Because it's very simple. Every node does the same, you add new nodes. There's some pitfalls, which you'll find out in if you don't read the Netflix tech. Okay. Yeah.
Could you just clear a very small question?
Yeah.
You said that if one node is trying to replicate over another data center, okay, and that node there is actually down, then it's recalled such a request, and when the node is recovered, it will set it again.
So what it will do?
Yeah. Why is not finding another one?
No, it would. If that it will find a remote coordinator that is above. Okay. Ideally, it will pick one that owns the data in that other data center. If it's not, it'll still ship it over there. And you know we're talking about hints. That node would keep it as hints until the actual real replicas in the other data center came up.
Could you give some idea of what the size of the Cassandra code is? It sounds very complicated.
It's huge. Actually, I just came back from San Francisco, where we had our company kickoff. I just joined this company, so it's quite new to me. And we actually had an entire day with a committers bootcamp. It's an open source Apache project. So most of the people, DataStax invite them over, and a good chunk of them do work for DataStax. And they actually took us through the code base, and it was basically like, how did I describe it? It was real computer science. Okay, they can't use the data structure which is in, say, it's in Java, the Java library. They have to make a specialized one. Okay, they implement a consensus algorithm called Paxos. Had to implement their own for their special use case. You know, if you look at how it stores data in memory before it flushes it to disk, to allow it to be very concurrent, it was using their own implementation of it was a copy on write array list. It's large. I'll put it there. You can go and check it out. It is. I don't know. I couldn't give you a number. I could guess, but it is rather large. But the only advantage to that, something that isn't a downside to it, is it's a large code base, but it's one process. Okay. So that thing, if you're a Java developer and you check it out and you build it in Java and run it, that's the only thing you've ever run anyway. That one Java. Okay. It's actually a bunch of jars, but right. Yeah. It's a very interesting database.
What I'm just wondering about is what the sort of the client side is like. You alluded to the fact that the client constantly has to keep up to date with the the state of the distributed system.
Absolutely.
So does that mean that there is some sort of a daemon or well, I mean, that then the real client has to connect to our, I mean,
No, so it's not like, say, Mongo, where it has a daemon kind of managing sharding. You know, where you have I forget what the phrase is. So the protocol between the driver and the server is two-way. So it used to be, if you've used an older version of Cassandra, it was very RPC, I'm going to send you a query, give me a response, please. The later versions of the drivers, they have this protocol where they're constantly chatting. So it's very much it's not a poll model, it's a push. So as new nodes are added, and say I've found out about a new node, that particular server will tell the clients that are connected to it, hey, there's a new server. So he's constantly keeping a state. And there's actually a table inside Cassandra that you can look at, which is, you know, who it currently thinks is the seeds. You know, sorry, not the seeds, that its peers. And the client can, if it wants, do a query on that and just find them out. I'm going to show you, there is like a section on the client, but mainly the programming point of view rather than the management.
yeah, but I mean, that still means that the client is not just like a JDBC.
Oh, no, the clients in these type of things are more complex. Yeah. The clients are open source, and it's one of the big things which DataStax has done over the last year or two, because we used to have a lot of people contributing to Apache Cassandra, but then the drivers were built by various companies who you know used it, but then if they stopped using it, the drivers went to disrepair. Okay, DataStax has made an effort to basically make a standard set of drivers that all like have similar programming interfaces and that are tested against very large clusters, you know, every release. And again, they're open source. If you're a Java fan, it uses Netty for this, and what do you call it? So it's non-walking I/O. And so essentially, one of the big problems with the old drivers was they were very much request response. They were RPC. Okay, so if you needed to do 1,000 concurrent queries to a Cassandra node, you needed 1,000 connections, TCP connections. Okay, the later drivers, they're all kind of this asynchronous way they keep chatting to each other, and they can actually they all run concurrent queries with sequence ID. So over one TCP connection now, it will run up to 32,000 concurrent queries, and they generally all keep one connection open for like information, like what's happening in the cluster, that type of thing, and one connection open up for queries. You can make more if you happen to do more than 32,000 queries per second. That's the one node if you attach 10 nodes. You can do 300, a lot. Any more questions? Yeah.
How much overload does this protocol between client and service takes? Do you have an idea? How much does it add to the ordinary user case?
So I'm going to say it's very good now. It's a binary protocol. So it is pretty much, it's a custom binary protocol. It's pretty much going to get as small as your query going that way and how much data you're actually transforming that way. And if you want, you can compress the data across the stream. And again, it's spec'd in a way. So you can read the spec of the protocol. That's how people still continue to build their own drivers if they want to. Netflix have their own driver because it's such an extensive use. Yeah.
Does the replication mechanism that you described for the transactions apply equally to the gossip and the state information as well, or is that not applicable?
So they're very different things. So it's a completely different. They don't use, say, the public interface to talk to each other. They have their own way of speaking to each other. You don't know really anything about that apart from which ports open up. You can go and look. It's open source. You're more than welcome. But the gossip protocol is, I don't know a huge amount about it apart from it talks to the right and sending it out to replicas. So you don't send like data over the gossip. That's just like status, let's say. Any more questions before we move on to the downside of Cassandra? Not the downside, the new thing you have to learn. You're not going to get this running a 1,000-node cluster across 3 data centers around the world and getting 1 million writes a second for free. You have to learn something. Actually, you get a lot more than 1 million writes a second there. It was 300, and these are Netflix's thing. There was you can read the blog and make sure I've not misremembered this, but it was It was 300 nodes, and it was 1,000,000 durable to 2 disks write per second. It was not like certain other databases that do their benchmarks in memory. Okay. So data modeling. What we're going to have to learn to use a database like this. Things are going to change, okay? You're gonna lose some of your favorite things. You are definitely not going to ever join your data. Why? Because it's now spread across many hundreds of nodes. Imagine you had 2 tables and they were both spread across 100 nodes. Just imagine how you would join that data. Think to yourself as a Cassandra developer. It's not going to happen, okay? If you want, I say the reason I generally find people use Cassandra, the reason I used it, is because we want predictable and scalable performance. So if we've got 100 gigabytes of data today, and we've got 100 transactions a second, and we want to times them by 100, we want to have 10 times tomorrow, we add the 10 nodes, we get the same response times. So everything designed in Cassandra, it has to be scalable, okay? And how does scalability work? It essentially works by knowing which node to go to, 2 if you want higher consistency, being able to go to exactly where your data is on disk and doing a single seek, or maybe 2 seeks. 3 seeks, but a very small number, okay? If we're ever having to join data across the network, anyone come from a Hadoop background, like analytics rather, Hadoop shuffles data a lot across the network. It's generally what the majority of Hadoop computers are doing all day. We can't do that. It's our operational system. We want the single-digit millisecond response times, regardless of whether we have 100 megabytes or many, many terabytes. So what do you think that means? How do you think you data model in Cassandra? Any guesses?
Denormalize everything.
There you go. You must denormalize. Okay, and it's scary and it's different. And I often get this response. I certainly had this response when I was first. I was like, I've learned all this, I've done it, I want a flexible data model. Then I kind of got a reality check of the data sizes I was working with when I was working for the company before Sky, which was Morgan Stanley. We had a trade stack, but it wasn't a large trade stack. It fit in memory on our computers. Suddenly we were dealing with hundreds of thousands of concurrent users, all with large sets of data. Okay, so once we get over the panic of that, what's the language that we use? Okay, so you are going to have to learn to model your data differently, but once you've kind of accepted that, you can reuse your SQL skills, because interacting with Cassandra does look a lot like an SQL-based database. This is both a good thing and a terrible thing. It's a good thing because you do not need to learn a new language. It's very similar. We have some different data constructs, we have some different types. The bad thing is, you hire people who just use relational databases and they think, I don't need to learn this, I know how to use this. And they start separating out into tables and then they start doing joins, but inside their application. Okay, and that's much slower. Okay, getting people to normalize is the hardest part of building a product, like something on top of Cassandra. Okay, but once we do, the CQL is not going to be surprising. So let's have a look at it. Does this look scary to anyone? It's not going to be hard to learn. You've probably seen things that look a bit like this. Or inserts, pretty similar, or selects. The difference being, what we're going to talk about is you can't select it. You can't, these conditions here, they're not going to be able to do everything that you could do in a relational database. Cassandra does have secondary indices, but you don't use them. I will talk on why you shouldn't use secondary indices, but essentially we're going to denormalize so that we can go directly to our data. You're not going to be able to see this because I've seen the resolution of this, but it has a lot of types. All the types you'd expect from a normal database, but quite a few more interesting ones. Okay, ones that you typically wouldn't use because it would be seen as an anti-pattern. As soon as you saw, say, what's an interesting one? A map, or a set, or a list. Someone would probably hit you with a stick and say, come on, it's a normal form. We're not doing that inside a relational database. But these types help you denormalize. I'm going to show you some examples. The other thing that you need to lose all hope of ever having again in your life in a distributed database is auto-increment. How could you imagine implementing a counter, a sequential counter in a distributed system? It's just not possible. Okay, it is possible. You'd use something like zookeeping, have a distributed lock, and you'd make all the nodes agree on who gets the next number. Does that sound fast and performant? No. So you're gonna get to love UUIDs. So rather than key things by a sequential number, we're going to use something unique. Okay, and this is a standard. No one's invented this. UUIDs or GUIDs have been around for a long time. we're going to use a particular type of them quite a lot, and that's time UIDs. Because if you remember, my kind of selling point, I'm not really selling anything because Cassandra is free, but essentially, Cassandra, you can pick how it orders things on disk, which is why it's great for, time series data, trades, sensor data, how often people have played, Game of Thrones on Wednesday, anything like that. And essentially what this means is when we data model things in Cassandra, if we tell it to order by a time UID, it will be both in the order of when it happened, and it will be unique. So we don't need to worry about IDs and all those type of things. Okay? Let's have a look at an example of a few of these different types. Let's have a look at collections. So this is videos. So imagine you were storing some information about video files. I wonder where that came from. Okay? What we'd have for videos often is, say, a map, because we have lots of different sizes of like thumbnails of pictures. Okay? We can actually keep them in here. Now, this is text to text. So I'm assuming this is a link to it, but you could have a blob in there and store actual, binary data inside Cassandra. So you wouldn't want it to be too big. Yeah? Alternatively, let's say we wanted to tag the video, we can have a set. Okay? Just like you'd expect in normal programming languages. This is where it gets even more interesting, because we're going to make you denormalize, and this is how we're going to make you do it. We're going to allow you to define your own types and have collections and sets and lists of your own types. There's an interesting one. Let's say someone had multiple addresses associated with them. You can create a type like this. And then inside your table, you could have a map of them or a set of them. Okay? And here's how we might use it inside the videos table. If you've ever done anything in that kind of media, you realize that there isn't just one video for your movie or your sport, your football game. There's many different versions of it for different screen sizes, different qualities, all those type of things. So this here is a set of all of the different, video metadata, the information about it. Okay? We can go crazy if we really want to. If we're going to store something like you have some JSON, okay? But you want to store it and you want to type it inside your database. Okay, for each of these, say, at the moment here, where do we have a list? Do we have a list? Oh, we don't have a list section. So we could have embedded, and then inside our schema, we can create these types. So this is actually, we've got multiple categories here. So that can be a list or a set. So it's a little bit different, okay? I'm not sure if anyone's ever used one of these, but you can just have tuples if you want. I always think to myself, I'd rather use a user-defined type and give it a name. But let's say you had some coordinates or something like that. You kind of use it. Okay? One final code. Yes?
How do you avoid collision in UID?
So, do you mean collision in UUIDs?
Yes.
So there are 128 bits. Okay, so I used to have a really cool statistic about that, but it was something to do with atoms in the universe, and we could use about it. There's a whole, if you Google, have a Google about conflicts in UUIDs. I once calculated if one of the applications I built that if we ran it for a few millennia, there's a chance, in a 0.00% chance we might get a collision. Okay. The same question often comes up about hashing, when we're doing the hash rings. And again, Cassandra used to use MD5 until people actually realized that it actually does have reason, collisions quite often, well, not quite often still, but millions. But if you're writing millions of events a day, suddenly it becomes more. But then that's why Cassandra moved to Mode 3. So there could be a collision. And if that crazy thing happens, you would essentially overwrite the data. Okay? The final type I want to talk about, and this is if you're getting into more advanced data modeling, but I'm just going to talk about it because it's often misinterpreted. Because it's called counter. So what do people think? I've got a counter, I can start using it as an ID. It's not that type of counter. And this is actually just taking the mick out of our own company. Because counters were pushed in by another company, because it's open source, right? Cassandra is not owned by DataStax, even if they do contribute the majority of the code. And counters for, say, statistics, or just like metrics, about, say, how many visitors you have in your website. They were added in by a certain company. I'll give you a clue. This data came from that company. Twitter, we're a big user of Cassandra. And they're pretty broken. They were pretty broken. Not when you were using them, but let's say you restarted a node and we replayed a commit log, which you have in most databases. It would re-add them on and do things like that. And then DataStax got some funding, and then someone tweeted, which was quite funny. Well, Hacker News tweeted, they raised 106 million to fix the counters because it was just a long-standing joke that no one used them because they were broken. Something else that's really good for time series data is TTL. So how many people have a cron job or some kind of batch job which goes and cleans up the relational database? It goes and deletes the old trades, or it goes. We all have them. You need them, okay? But every time you do a write in Cassandra, you can say it's going to be around for a week or a day. So if when we're keeping, say, stats on what people have watched, we don't care about what people have watched 6 months ago. We care about the last 3 months to do analytics on and things like that. So you can put a TTL on, and that data will just cease to appear after that time, which is surprisingly useful at times. There's a dev tool for it. This is built by DataStax, but again, it's free. It's open source, and it can connect to your Cassandra clusters, have a look at the schemas, and then give you content assist based on the tables you have. There's also a command line interface, which I tend to use more often, but whichever you prefer. So that's all the information. I was then going to go through an example, very similar to one I built. Has anyone got any questions about any of that? Everyone convinced they're going to normalize? Yeah.
You mentioned at the very beginning that it doesn't support group by and aggregate functions.
Correct.
But sometimes you do need them, but not in a business situation.
Absolutely.
What
So
would you do?
I actually have an entire slide there. So there are two answers to that question, followed by a dodge. Now, I'll do the dodge first. So we know why we don't do them, right? Because you have to scan the entire table. Not scalable. However, it's been pointed out, there's no technical reasons. We partition the data. Okay? We're going to talk a bit more about how we partition it, and I can actually delay it till just then, because it'll make a lot more sense then. But there's also another way to do it, and it's to run, who's heard of Apache Spark? Okay, so it's an analytics framework which has awesome connectivity to Cassandra, and then can suddenly do these things. But because you're doing them over a large cluster, slow. So you're not going to do it in milliseconds. You can do it in 10 milliseconds. You might do it in 100. If it's a big group by, you might do it in 5 minutes. Remind me, sorry, a question.
You mentioned earlier that how Cassandra handled conflict resolution. So if two people are updating at the same time, different nodes.
Yeah.
Even cover that well.
Okay, so we're going to talk. It's normally a data. I can tell you about the conflict resolution strategy, and then we're going to talk about in this example how we avoid it. Because if you were to, I have a talk on Cassandra anti-patterns. And anti-pattern number 4 is don't model your data so that you have distributed mutable state. And as soon as I ever say that, I think that sounds a bit stupid. Why would you ever have globally distributed mutable state? That's just not going to work. You're going to have race conditions. Okay, so when you data model in Cassandra, you generally data model immutably. So rather than storing a bank balance or a current number for how much we have of trade, oil, crude oil, whatever, we would store the transactions. These would have timing UIDs associated with them. And then we never actually write to the same field. Because, and you'll understand more when we talk about partition keys and clustering columns and data modeling, but you can essentially never overwrite data. And then what you end up doing, because obviously that would lead to the problems in event sourcing and that type of thing, you'd end up with a very, very large set of data. Then of course you can snapshot it. So let's say trading is an example, banking. You might have a trade and you want to work out, say, the balance or something, you would read them all out very quickly. They'd be stored in order on disk. That would be a quick read. We'd be doing one seek using an SSD even quicker. Okay, you then work it out inside your application. But then once a day, what you probably want to do is snapshot the entire of yesterday and just put that as one number. So you don't have to do it every time, because obviously that would eventually not scale. But we'll talk about that a bit more in this example, because we're going to do that. Any more questions? Yeah.
What do you use to represent the data on the client? JSON?
So what does the actual code look like?
Yes,
for
for representing data, like complex types, things like that.
Yeah, so I've got some examples of that coming up, so I might as well just show you that. I've got ones in Java, but most of the drivers have some form of object mapping. Any more? Still awake? It's late. We're getting on. Hopefully it's quite warm here. So the example we're going to go through, and hopefully we'll cover some of the things, is event store. It's time series. We're going to keep track of everything our customer's been up to. But you can see how this would be applicable, whether it was trades or, you know, online gaming, or, but this is the real example of how Cassandra can be used at a really scalable level. And it's something we did very at Sky. Not quite the same as this, because I don't work for Sky anymore, they wouldn't let me use it, but it's similar. Okay, so we have customer events. What are they up to? Easy, Chris Batey. We want to know everything they've ever done. Okay, this could be because call center staff, they want to ring up and complain. We can see what they've done the last 30 days. Or then we may use it later for analytics. We might say, oh, these many customers have watched Batman on a Thursday, so we should put a promotion on for Batman 2 on next Thursday. Who knows, okay? But we're going to keep track of what they're doing. The other type of thing this was used for was billing. Okay, so we can see how many times they listened to a song, watched a movie, etc., and then you can send them a bill. So it needed to be durable. Okay, so we couldn't use any form of in-memory structure or something that doesn't take a database that doesn't take durability seriously. We're going to bill on it. Okay, we need to keep all the original data, or at least until we build and so many months have passed. That's because people get upset if they argue their bill and we're like, meh, we think it was that. Okay. For each of these customer events, we're going to associate some other pieces of data, like which staff member was involved in this. Okay. Or we're also going to keep track of which store. So the last company I worked at, we provided the same products via mobile apps, websites. You could go into a store, that type of thing. Because eventually we want to work out things like, oh, which one's the most profitable, which ones people are using the most. However, we're just going to talk about building the operational side. If we wanted to build the analytics side, we need Spark. Okay. So the requirements we've got, we want to be able to get all the events out. Okay, that's to give to our, that previously actually was to give to our analytics system, but with Spark we actually wouldn't need to do that anymore. We want to be able to get all the events for a customer, so we can see what they've been up to and send it off to some processing to see if we can give them any offers or something like that. We want to be able to get them for time slices. This is the example to say if they rang up the customer service, or we just wanted to see what customers are up to. Okay, this is how we model it in Cassandra, right? Yep. Anyone going to disagree? We're going to have 3 tables. We're going to put some information inside the stores, some information in staff, and we're going to have some customer events up there. So we're not going to do that because, if you remember rightly, that's not going to scale. Okay, because if we did that, it would be separated across lots and lots of nodes. So we're going to model it just like our queries. So if you have children, you get them to model your data because they'll probably do it right. Okay, they won't try and do clever things. They'll say, you want to read it like this, or your dashboard on your website looks like this. I'll just store it like that. Okay, which is pretty much what you have to do. And of course, everyone gets upset, but then we remember that our data set doesn't fit on a computer, and that's why we're using something like Cassandra. So here's a more realistic model in Cassandra. And hopefully we'll touch a bit more on what you were saying, asking you. So we're going to keep it all in the same table. If we were going to store more information about the store, we'd use one of those user-defined types, but I wanted this to fit on the slide. Same for staff. Okay, imagine that was user-defined type, or we just kept lots and lots of things about it. And the important thing, the only thing that you can really do wrong in Cassandra is to get this wrong. Is the primary key. Okay, the primary key is where you get to pick 2 different things. You get to pick which data lives on the same computer. And of course, data that you query, say a time slice for what the customer's been up to, we want that to be on the same computer. It will be on 3 or 5, depending on how many replicas you have, but we need it to be on 1. The first part of the primary key is exactly that. You can put as many fields as you want in there, surround them in brackets, and all that data will live on the same computer. The only thing you have to worry about is it not being too big, because it has to fit on a single computer. So we can talk, if people get really interested into data modeling in Cassandra, then you might decide that one customer might do too many things. You know, let's say they'd have 6 gigabytes worth of events, but we can talk about how to do that. The rest of the primary key is called the clustering columns. This is the part that lets you pick how it's ordered on disk. Okay, so you're going to have, in your queries, you're going to have to include this, right? And you don't have to include anything else if you don't want to. Okay, but if you want to filter additionally, it has to be by this, and it has to be 1 range slice because we want to do that fancy thing where we sequence, read it off. And to touch back on your question about, let's say we did need to do some aggregations, because they're not supported in Cassandra. However, there's no, and for the reasons we've discussed, but there's no reason why aggregations in Cassandra should not work for the same partition, right? Because they're on the same computer, right? They're not supported, but there's no technical reason why they shouldn't be. Aggregations across the entire table, never going to happen. Or if it did happen, slowest feature ever, okay? If you look at Cassandra 3, which is not yet released, there are people working on user-defined functions that run inside the Cassandra server. You define them in any language which the JVM's, I forget what it's called, the scripting component of JVM. So it can be JavaScript, it can be Java, it can be Scala, it can be many, many languages. And you get to send them over. You get like that create type, you'll get to create function. So you can actually then do really efficient, depending on how big the row was, you know, aggregations across things with the same partition key. Make sense? But not yet. If you want to do them now, you need to use something called Slack. And I can, if you want to talk about that after, we can, but it's a whole talk in itself. Right. So this is the command line tool. So we haven't used the GUI tool here. And it colors them out for you, just to remember that they're important. I try to use the same colors. Okay. This is our fancy time UID. So inside there, it's embedded the time, and it's unique. Or the way they work is that they're pretty much guaranteed to be unique if they're generated on an individual computer at that time. You can't, well, you could, but you shouldn't retrospectively create time UIDs for things in the past, because that computer could have generated that time UID at that time. Right. Okay, so they're going to be in order on this by this, so we can do really fast slices. So has anyone ever heard of the term like wide row or columnar database? It doesn't look like a columnar database, does it? Cassandra is a wide row columnar database. It just doesn't look like it. It gives you the programming API you're used to. But what it really means is when people talk about wide rows, they're talking about things with the same partition key, because that's one big sequential thing on disk. And to put that into a picture, this is what it looks like from the developer's point of view. I'm used to that. I'm used to using any kind of table database, any relational database. However, we've actually only got two, I'm going to call them storage rows rather than, you know, table rows. We've only got two different customer IDs. So in reality, there's only two long things on disk. And we guarantee that Charles is on one computer and CH Batey is on one computer. So what that looks like on disk is more like this, two rows. So we get the wide row. And all of these, so and you've also noticed is I haven't included the time. One, because it's really big, and it wouldn't really fit. But other, because the time is used as part of the, as basically is used for the ordering. You do get it back, don't worry, it doesn't vanish, but I just couldn't fit it on the slide. But it's essentially meaning that within a single partition, say Charles or CH Batey, all of the different table rows are in the same storage row. Okay? Makes sense? That's the big difference. Not many databases really tell you how they store it on disk, but it's super important if you want it to be scalable. Okay? A couple of other things to note if you've ever actually like used a lot of relational databases is we can miss out these columns. It doesn't matter. Okay, so you don't need to put them all in. If there's no varchar 256, you know, it was just text. And that's because it's just stored on disk. It's not one of those tabular tables where it allocates 256 bytes, even if you put Chris in it. Okay, so it's somewhat more efficient on actual disk storage as well. But that's the magic of Cassandra. And when you actually think about it, it's not really that magic. It's somewhat sensible. It's just done at large scale and works pretty well. Yeah.
How does it avoid like fragmentation?
Exactly. So there's so much to talk about in Cassandra, but yeah. So here's where the question was, how do we deal about fragmentation? Because you're like, what happens if this one comes in third? Yeah. How would I get it in there? And the reality is one of the reasons Cassandra is such an easy operational database is everything it puts on disk is immutable. So what is a backup in Cassandra? Take the files. There's no fancy things going on there. But that means that when you write data in Cassandra, it ends up on a commit log. That's your durability. Okay, so just forget about that. That's just durability. You can turn that off if you want. Don't. And then it goes into memory in a mem table. That's an ordered structure. Okay, that is, can't remember which type of tree, but it's ordered. Then when certain memory pressures hit, flushes it to disk, sequential write. Fastest thing a disk can ever do. And the disk is always the slowest thing on your computer. Okay? Now, what happens when the next lot of data comes in? Exactly the same thing. Memory builds up, flush to disk. Then, a bit like garbage collection, in the background, compaction happens. So we've got two immutable files for the same table on disk. Okay, what it'll do is those two will still serve as reads, but they'll get merged into a new file that will be built. Those two will be deleted. But as it merges it, it will merge it in memory in order. Any more questions on that? Because we're about to jump over to what you're asking, which is, what does this look like in code? No? Everyone's still awake? This is the long, oh no, one more question.
Not about the last thing, but when you show this Cassandra create table example, is it possible some way automatically or semi-automatically to create from the relational database?
So,
because both are texts, right?
So the way that there are a number of different ways. Most people who use Cassandra are migrating either from a relational database or Mongo. That's like the two. That's where all of Cassandra people come from. A lot of people, a whole migration strategy is without downtime is obviously something which you design around. But there are a couple of tools. You can export obviously your relational database to select text, one of the things, and you could write the code to take it, put it in. Apache Spark, and I have these examples because I've had to do this before, is something which can connect to a relational database, connect to a Cassandra cluster, and slowly stream the data across. So with a reasonable amount of operational complexity, because you have to have Spark and Cassandra, you can move like millions and millions of rows with very little effort from, say, MySQL to Cassandra. Yeah. Any more questions? Last part. So I actually think this is the least interesting part of Cassandra. But people want to see some code at some point, right? But it is. Has anyone used JDBC? What languages are people? Are we C, C++, Java, Scala, Clojure? Okay, if you've used anything like a JDBC driver or anything like this, this is not going to be exciting. I apologize. You know, imagine once a table there. There's only so much we can do, but I will take you through it. So there's two categories of drivers. The ones DataStax make. These are quite new, and it's basically DataStax builds products on top of Cassandra. It builds supported versions of Cassandra. So for DataStax to exist, we need people to use Cassandra and then eventually decide they wanted to support one because they work in a bank or a large media company called Sky. Okay, but they suddenly realized that drivers were getting a bit out of date. You know, if people stopped using Cassandra or they stopped using new features, why would they extend their driver? Some of them are open source, so we could jump on it. But in reality, eventually we decided we're just going to build a solid, well-tested driver for the main programming languages. And the community other people can still have their own if they want, or they can base it off theirs, because they're all open source. So other drivers, especially some of the other JVM drivers, like the Scala and the Clojure, most of them now build on top of the DataStax Java driver. Okay? And they've also got a reasonably similar programming API. Mainly around the things like those load balancing policies. Remember, that wasn't Cassandra, that's the driver deciding about load balancing, right? But you can do similar things in each of these ones. And we're going to have a look at the Java one, but they're all very similar. So it's all on GitHub. Everything's on GitHub now, apart from Apache projects. No, they are too, because they're mirrored from Apache. You know, but most things are on GitHub. You know, two components. You either just want the raw one where you're going to execute the CQL. Okay, or you want to do a bit of mapping. So anyone uses things like mapping APIs like Hibernate and things like that, it's not like that, don't worry. That's not too bad. It's a very light mapping API, because there's one thing that's extremely important when dealing with a database like Cassandra, is you understand what's going on under the covers. You want to make sure you get the right partition keys, the right clustering columns, otherwise you will not have fun. Okay, I think is there a JSR, like a standard, you know, being proposed for Java for NoSQL databases, which I find baffling because it's a standard for databases that you do different things. Okay, we denormalize, we duplicate data, we want to model it, you know, exactly how we're going to pull it out on disk. I don't want to be hidden away, but there is a nice little mapping API if you get sick of writing boilerplate database code. So essentially, you have a session object. You're just constructing that with a, hosts and ports and things. You don't need to tell, when you construct these objects, you don't need to tell it about your whole Cassandra cluster. That two-way protocol, it will talk to a number of nodes, and it will find out about the rest and find out what data centers they're in and all those type of things who it should be speaking to. Once you've got hold of one of those session objects, it's really quite boring. Okay, actually, all of this is just Java 8. It's not anything exciting to do with Cassandra. This thing returns a result set, which you can, use the Java 8 stream API, or this could be, if it looked a bit more like JDBC, you'd just see like row.getString, get UUID. It is a typed database, so you need to put it into a typed object. And my assumption here is that this customer event looks like this. It has these fields. Okay, that's a normal query. So where you're passing in the text into Cassandra. Okay, so that's going to send that query over to Cassandra. Cassandra's going to have to parse it, work out which tables to look in, and send you back the data. You're probably used to things like prepared statements. Very similar, except this is a working application you can take from GitHub. But essentially, this bit of code with the post construct annotation is going to execute once. Okay, that's where we prepare the statement. It sends it to Cassandra. It parses it and sends back a unique ID. And then each time the driver then sends it, it doesn't need to send the whole text. Cassandra doesn't need to parse the text again. It understands the query. You just stick in some different variables. So here we bind the customer ID. So this is our example where we want all events for a particular customer. Then we use the exact same mapping function because the data we're getting back is the same. Okay, and we turn it into a list of these customer events. There's a slightly different API if you don't like passing strings into your code. There's a builder API. So you can build like a query which says I want all the rows from this key space with this table. I've got an equals here, so this is my partition key. And then I'm doing a slice query. So we're doing it on time, because remember that was our clustering column. That's the thing we're allowed to do slice range queries on. This thing's here is just a little thing you have to do, because remember, the type of time was not a timestamp. It was actually a time UUID. So this is just how you say, start of this to end of this. It generates the UUIDs that fit on the very edges. And then we use the same mapping function. Not particularly exciting. If you get sick of writing code like that, we have the mapping APIs. So this is where you just create the class, you annotate it up, you tell it which columns each field map to, you tell it which is the partition key in the clustering columns, which is why I don't mind this mapping API, because you still have to understand. If you got dropped into a Cassandra code base and you saw this class, you'd probably think, what's a partitioning column? I want to show you, that's not even a real thing. A partitioning key or a clustering column. And hopefully you go to Google and ask, what is the partition key? And you would find out, and then you wouldn't make mistakes. And then you just annotate up an interface. So if you've used Spring Data or Hibernate, things like this will be quite similar. So rather than having to write the boilerplate code which maps them, you just have to tell it the queries. So it's not going to work out what the queries are for you. You have to do that, okay? That's the difference when you're working with Cassandra, because you can only query it in a very limited way. And then to create one of these, you just create a mapping manager and a couple of lines of code. But I hope you agree it's not very exciting. If you've got text in the database and you want to map it to, say, an enum, this is only going to be that relevant to people who program in languages that have, support for things like enums. Then so store type, online, retail, franchise, mobile. Those fields inside the Cassandra database will get shoved into this field, and you'll get an error if Chris was in there because it doesn't match the enum. Okay. The user-defined types are the more interesting things, because that's not going to map to a Java string. That's not going to map to whichever language you're using, like a built-in type. So perhaps this store example is one I use. Perhaps you want to store more information than just the type or the name of the store. We've got a bunch of fields. So here what did we do? We wanted, so frozen just means it's immutable. We want this, we tell it it's a store here inside our tables, create this type. It's in there. And then it's hopefully going to be not a great surprise that inside our mapping API, we just put a store instead. And Cassandra, the driver, rather than Cassandra, will put it into this Java class for us without us having to write that mapper of get string, get UUID, that type of thing. Okay? Any questions on that? Yeah.
The frozen annotation. What
Yeah, the frozen one.
is?
So frozen in Cassandra, so we've got these defined types. They were Cassandra 2.1. What frozen means is you can't update, say, just name. Okay? If you want to change the store, you have to provide a whole new store. That's a limitation of Cassandra. You have to update an entire user-defined type in one go. The reason there's a frozen keyword is in the next version of Cassandra, that limitation is going to be removed. So they didn't want to break old SQL, old like data definition files. So you explicitly have to make all user-defined types frozen right now. Then the next version, you can remove them if you want to say do an update statement, which just affects say this type rather than name.
Do you have an insert example?
Pardon?
Do you have an example of an insert statement to insert the data to the database?
Only many slides back. Are you curious what user-defined types look like?
Yes, I was just wondering how do you represent like something like a star? Do you represent like as a JSON or
It is
like
as close to JSON as you could imagine. And there's a new feature coming in Cassandra 3, which basically means, let's say you've got a user-defined type inside your schema. Rather than have, and let's say you receive some JSON into your application. Rather than have to turn it into an object to persist it into the database, you could actually just put some JSON. You can actually just give JSON to Cassandra. It's like insert. It's not finalized yet. It's not released. It's open source. You could go and affect it by saying that's a terrible syntax. But it's going to be something like insert JSON, JSON blob, and it would have to match. Your user-defined types would have to match the JSON. But you can then remove a lot of boilerplate code of. Oh yeah. So we're pretty much done. Hopefully you get excited about Cassandra. It's fun to build systems with Cassandra because you're normally building big systems. We do have some people though, because like we have one person who came to a meetup recently and gave a talk saying it was Cassandra for the small scale. And they didn't have a big use case, but the reason they wanted to use Cassandra was they wanted to have 2 nodes with a replication factor of 2, and it's basically because they couldn't be bothered to make an existing database highly available. Highly available in the sense you can use 1 node, but it's like, oh, we don't care. We use replication factor of 2. We know we could do joins if we wanted with a different database, but in general, most people who are using Cassandra, they're normally migrating from a project which has hit its scalability limits, or they've had their data center flooded and they realize that they do need to be active across 2 data centers. So anything driven by the web or anything driven by devices, there's enough humans to generate a lot of transactions per second. Yeah. I can just run through a couple of other little things, a couple of other nuggets that you would need to do if you're going to play with Cassandra. One of my favorite is query tracing. So if you're like, remember that animation I did with the replication? You can actually just watch this in query tracing if you want and understand what it's doing. Okay, so you can see. Don't worry about the exact example here. It's only a 3-node cluster. It's not that exciting. 3 different IPs, but you can normally work out if your queries are good by looking at the trace. If your queries need to go to 24 nodes to satisfy, it's probably not a good. You've probably not data modeled or picked your query very well, and it's not going to be quick. So query tracing is extremely useful. The other question I get a lot is, you have to denormalize, right? Let's say we wanted to query by different fields rather than customer ID. So I'm going to store it twice. Okay. A lot of people talk about inserting that denormalized data atomically because they want it to be there in both or in neither. Now, there's no isolation in Cassandra. It's a distributed system, but there are batch statements which are there to basically say that if we've accepted this right, we will keep doing our best to retry it until it can end up in both tables. Okay? And if you're interested in exactly how that works, I might have an animation. I do. That's what the code looks like. You have 2 statements, you put them into a batch, and you send them in. This is considerably slower. This is the 1% of your application. Okay? And I have a funky animation about how it does it if people are interested, but it's been quite a long evening, so you might want to stop there. Okay, I'll do the little animation. No one's run away. How it achieves this, okay? You're not going to get atomic, you're not going to get acid in Cassandra. But we can do like a best effort at making sure a set of statements have succeeded. Okay? And it does this by, you do a write, and you're going to work out why it's slower right now. Before the coordinator says it's done, before it tries to actually write it to people, it actually gets a couple of buddies and it says, we're going to make sure this works, guys. And it's called a batch log. So now there's 3 nodes working in conjunction to complete this query. Let's say this is 2 inserts, 3 inserts, okay? Now is the earliest point that success could come back, okay? If you had a consistency level or 1 and that was the coordinator there, okay? And then it does the normal replication. The difference being that if this coordinator crashes, before it's applied it to all of the replicas, these guys will take over. But it's considerably slower, but some people really like it because they're duplicating their data and they want to, make sure it's not in one of their tables and not the other. Okay, I did more data. Another is lightweight transactions. So we generally don't want ACID transactions. You might want them, you're not going to get them in a distributed system. Okay, someone might claim it, they're probably lying. Okay, but what you can do in Cassandra is we call a lightweight one, more accurately probably described as a compare set. Okay, so this is, let's say for some reason we ignored my data modeling advice and we had a mutable field for bank balance. Okay, we wouldn't really do that. We'd record the transactions and they'd be immutable. But let's say you just ignored me. What you can do in a lightweight transaction is read it, see it as 52, and then write it and make it, say, 54, only if by the time that write makes it back, it was still 52. So we're going to look like Cas. Again, much slower, because all of the 3 replicas, or 5, or however many replicas you have, then need to communicate to agree on the write. Considerably slower. If you like reading computer science papers, it is a particular implementation of Paxos, which might be changing in the future, but and that's pretty much it. Cassandra is quite a hard database to do an introduction to. Or you would, if I just did an introduction of what you did with it, you would end up saying, well, how would that work? So you kind of have to go into a bit of depth. So sorry about the very long talk. If you have any questions down the line, you want to ping me. It's kind of my job to help out Cassandra users now. So if you've got any questions, I haven't got my email, but I've got my Twitter, so you can ping me and ask me for my email. We can chat. So well done. You've been Cassandra-ified.
Well, thanks very much, Chris. I think I realise it's been quite a long one, but I think everybody was engrossed. If anybody wants to come afterwards, we'll be going to the bar, Champagne Charlie's. Is that right, Jeff? Mm-hmm. If you're free, Chris, we'd love to buy you a drink and maybe rehydrate you. Yeah.
Actually, I've got a question, some help. If you were to skip out a section of that talk, say if it was an hour talk or slightly smaller, which bit did you least think, I don't really need to know about that? I'd look into that later if I cared. I won't be offended.
Yeah, the programming bit.
Yeah, not interesting. It is pretty true.